Course 3, Lesson 101. We are looking at both Lesson 101 and 102 today. To start out, we'll look at this geometric probability. So being able to look at a geometric figure that has different parts to it and saying what's the probability of getting in those specific parts of the shape. So finding the probability of geometric events is based on finding the probability of both what you want and the probability of the entire geometric figure, and then dividing. So for example, if we have kind of a dartboard, if we want to hit the bullseye, it's going to be harder to hit that than just the whole target, because we have the original, oops, sorry about that, I was trying to draw. We have the entire target, that circle, and then we have the little bullseye in here. And we have different sections that are worth different points, right? Well, it's much harder to get in that bullseye portion than in the rest of the pieces. So we could talk about the probability of getting in that piece. It would have a small percentage. So let's look at these targets. So in these ones, we're talking about the area of the bullseye. So just as examples, we don't have any dimensions actually on here. What we would be saying is that out of this entire region, for this one here, out of the entire region, this is 1/10 of it, okay? Maybe it has an area of 1, whereas the rest of it has an area of 10. We can say that it's a probability of 1/10 to get in this piece right here. Whereas being in both of these rings, maybe it's a quarter, okay? Maybe we're saying that both of those rings added together is 2 out of 8, okay? Something like that. Or if you just want to get in the target, the whole thing is just a probability of 1, because in geometric probability, we would say you're always going to hit the target. It just depends on where you're going to hit the target. Now, of course, with human error and things like that, in real life, we don't always hit the target, but in geometric probability, that's kind of the basis that we start off at. So if we have this figure here, so if a 12-inch diameter target is hit, what's the probability that the 4-inch diameter bullseye is hit? So basically, we want to know what is the area of the bullseye compared to the total area of the target. So let's just keep it in terms of pi here. So in the first one, we have a diameter of 4, which means when I do pi r squared, I'm going to do pi times, well, my radius is 2 squared, over the whole area of the target. If the diameter is 12, that means that I have pi times 6 squared. So I get 4 pi over 36 pi, which means the pi's can cancel out here. Okay, those are the same number divided, so we could just get 1. And 4 over 36 is 1/9. Okay, now of course these aren't drawn to scale, but we would say it's 1/9 of a probability if I hit the target, it actually gets in the bullseye. Let's look at some other examples. This is a pretty quick lesson here. Okay, a couple more examples. What's the probability that an object that lands in the circle also lands in the square? All right, so I need to say, if this square is what I'm trying to get to, what's the area of that compared to the whole area of the circle? So we are saying that the square is a 10 by 10, so that would be the area 10 by 10, over the area of the circle, which it looks like the diameter is 20, so we say I have pi times 10 squared, which it ends up that we get 100 over 100 pi, the hundreds cancel out, and I end up with 1 over pi probability of getting in there. It's a 1 over 3.14 and so on, meaning it's like 1/3 of a chance to get in the square if you hit the target. Another one, probability that the object lands in the larger region. If it lands in the larger region, will also land in the smaller region. So I want the area of the triangle over the area of the square. Well, the area of the triangle, I do base times height divided by 2. So 48 divided by 2 is 24. And the area of the square is 100. So I can say, let's see, this is 12/50ths, or even simpler, 6/25ths. I have a probability of 6/25ths of getting in the triangle. Okay, let's try this other one. area of the smaller one, so 12 divided by the area of the bigger one, 48, meaning I have a quarter of a chance of getting in the smaller rectangle here. Okay. Once again, we have a smaller square, so the area of that is 110 by 10, and the area of the larger one, 14 by 14, let's see, 14 by 14, it's been a long day, let's see if I can do that in my head, we get 196, of course, and we can simplify that to 50 over 98, and we can divide that again. Let's see, we get 25 over 49, which I think is the simplest we can go. All right, so we can say that I have a 25/49 chance of getting in the small rectangle compared to the large, or the small square compared to the large. Okay, and let's try once again the small from the big. Okay, and so it says that the radius of the small is 6. So if I do pi r squared here, I'm going to get 36 pi over the radius of the larger is 10, so we get 100 pi. Well, the pi's cancel out and we get 18/50ths or 9/25ths. Okay, it's a 9/25ths chance of getting in the smaller circle. Okay, now the question is, we've been doing the small compared to the big. What if we did, I want to know what's the probability of going on this outside portion rather than the inside? Well, something similar is going to happen, but there is an extra little step. Okay, so we said the area of the square was 100 centimeters squared. The area of the circle, okay, we said was 100 pi. Well, what is the area that is just outside? Well, that's the whole thing minus the square. So I would say that is 100 pi minus 100. That's the outside portion. Okay, that's the filled, this portion on the outside of the square. And then I want the area of the total, which is 100 pi. Now, so that we can actually get a simpler answer here, if I do 100 times pi, 3.14, I'll get 314. So 314 minus 100 over 314. So I get 214 over 314. And of course, this can simplify. So 214 can go to 107. And 314, let's see, 314 will give us 157, which I think that is as simple as we can go. But I have a 107 over 157 chance of getting on the outside of the square. And we can do this with any of the ones that we just looked at. So say we go back to this other circle one, and maybe I want to go and hit the ring outside of here instead. Well, what I could do is say, what is the area of that ring compared to the total? Well, the area of that ring would just be the area of the total, so 100 pi, minus the area of the smaller one, 36 pi, which means the area of this small portion would be what? 64 pi. So if I have 64 pi out of the total 100 pi, well, I could simplify that and get my answer, which would be, let's see, 32/50ths, so 16/25ths. So if I want to get into this ring, it would be a probability of 16/25ths. If you notice, probability of getting in the small center is 9/25ths. Probability of getting in the ring is 16/25ths. Makes sense that those add up to 1. Okay, that's how it should be. That's how it always should be. Okay, so that's geometric probability, saying what portion do I want to get in out of the total, okay? The part out of the whole. Now we're going to switch gears into lesson 101, which is about growth and decay. So let me just bring up that lesson here. So growth and decay, we're going to be looking at how things exponentially grow and also using the rule of 72 in order to figure out how long it takes for something to double or how long it takes for something to be cut in half if we're talking about decay. Excuse me. So remember that geometric sequence is what growth and decay is based on, and it's because we have these constant ratios. So if I have the sequence 1, 2, 4, 8, 16, 32, I have this ratio to say, well, I can take my two numbers, 2 and 1, and I can say, well, that is 2 over 1. That should be the same as taking 4 and 2, and 8 and 4, and 16 and 8. It ends up being that all of these are just 2, meaning that my ratio is 2. Okay, so it says when the constant ratio is larger than 1, okay, so in this case 2, would we be increasing or decreasing? Well, if we just based it on this pattern, this ratio is bigger than 1, and it looks like it's increasing. And this is true. If the ratio is larger than 1, then the terms are increasing. Which means if we have a ratio that's between 0 and 1, the sequence terms are decreasing. Okay, so if I have something like a ratio of 1/2 or 1/4, those terms are decreasing. So if I take something like this, 128, 64, 32, 16, and I looked at all of these ratios, so 64 over 128, 32 over 64, 16 over 32. Well, that means all of the ratios are 1/2. And just like we saw, this is decreasing. Okay, so that's the first one we have is exponential growth. The second one is exponential decay. So we use this for growth and decay, and it has a lot of real-world applications. So we use it in the financial and business realm. A lot of bank accounts have different compound interest rates, which is growth. Inflation means we decrease the value of a dollar, which often can be shown as decay. And even in science, when we're talking about organisms and how much they decrease or maybe increase and multiply, can often be modeled with growth and decay. So let's look at an example. The population of a country has grown 2% per year for the last 5 years. If the country's population is now 1,200,000, what will the population be in 3 years at the current growth rate? Round to the nearest thousand. Now, we just did an investigation on this in the book and found that if we're talking about compound interest, which really is the same thing here, our current value, okay, V for value, is equal to the principal, meaning the beginning amount, times 1 plus the interest rate, all of that to however many times you are compounding it, however many years we are given. So if I want the value of this after 3 years, I would say my initial amount, okay, that principal is 1,200,000. And then I have 1 plus my interest rate of 2%, which I'm going to show as a decimal, 0.02. And all of that is to the third power, since we want 3 years. So we would end up saying that I can plug this into a calculator and calculate what it is to the third power. Now, the reason that we have 1 plus this interest rate is because I want this original 1,200,000 and just want to add 2% on top of it. So if I go ahead and plug this into a calculator, which I'll bring up a calculator here so that you can see. So I can plug in 1,200,000 and say I have 1.02, so my 2% growth for 3 years. We would see that it will grow to be 1,273,449 people. Okay, so it's grown a significant amount in those 3 years. Now, our next question here says, using the rule of 72, about how many years will it take for the country's population to double? Well, the rule of 72 says if I take 72 and divide it by my interest rate, okay, excuse me, I can figure out how many years it will take to double the amount that I initially started with. Okay, so this will give me the number of years to double. So in this case, if I say 72 divided by my rate, my growth rate of 2%, means that I'm going to double this amount of people in 36 years. So let's prove that. And of course, the rule of 72 is not perfect. It will not always be exactly now 2,400,000. It's going to be close. It's a good estimating tool. It's not perfect though. So let's try it again, and instead of that 3 in an exponent, we're going to have 36 as an exponent. So I'm going to just copy this down really quick and change this to be a 36, because I want 36 years of growth, which means, yes, we get just about, it's a little bit bigger, okay? So it's not quite going to be 36 years, but it's going to be really close. We have 2,447,864, which is double the population. So it did take 36 years to get there. All right, let's look at another example. Here we go. The school in an older community experienced a decline in student population of 3% per year. If the decline continues, and there are 5,000 students currently, how many students will be in the community in 3 years? So we're going to use that same formula. We're going to say I have my initial amount, my principal, 5,000, times 1. Now, in this case, since we're not growing, I'm not going to say 1 plus 0.03. I'm going to say, since we're declining, 1 minus 0.03. And I want that to the third because I want 3 years down the road. So really, I'm going to be entering in my calculator 5,000 times 0.97 to the third power. Now, we'll plug that in a second. But the second question here says, how many years will it take for the student population to be cut in half? Now, the rule of 72 is often used for just doubling, but it can also help us with half-life as well. So if I use 72 divided by my rate of decline, 3, I will see that in 24 years, it should be about cut in half. Okay, now the rule of 72 is based on logarithms that are learned in higher math, but it's not just some random 72. It's based on many, many patterns and research by mathematicians. So let's look at these in a calculator. So after 3 years, my 5,000 people, 5,000 students, were declining by 3%, so we'd put 0.97, and that is going to the third power. So we see that in 3 years, we're only going to have 4,563 students. And in 24 years, we should have that 5,000 cut in half. So let's try it again. 5,000 times 0.97, all of that to the 24th power. And we see that, yes, the population has been cut in half. It's a little bit lower. Once again, rule of 72 is just an estimate. But we see that, yes, our population has been cut in half to be under that 2,500 students. All right, let's just look at 1 or 2 more examples. We'll do this one quickly. Carbon-14 is a radioactive isotope occurring in nature. It's used to date material, such as once living plants and animals. It has a half-life of 5,730 years. So someone has taken this rule of 72 and said some amount of decline equals 5,730 years. Okay, so they've figured that out. We know how long it takes to decrease it by half. So if we have a bone that is found containing about 1/4 of the amount of carbon as modern everyday bones, how old is the bone? So let's just make a table and think about this logically. So if I have a number of years, okay, I'm going to have a certain amount of carbon. So if I have 0 years, okay, this bone is new and fresh, it's going to have the full amount of carbon, 1 representing the full amount of carbon. Whereas if I take 5,730 years down the road, it only has now half of the carbon. Okay? Now the question is, all right, we're getting closer, but we only now have 1/4 of the amount of carbon. So if I have halved it from here to here, and now halved it again, that means that I have also had another 5,730 years. So if I say 5,730 times 2, I will get how many years it is until I have just that quarter amount of carbon. So if I have this bone that only has a quarter amount of carbon, then it's probably, we can estimate, it could be like 11,000 years old, potentially, okay? That's how they kind of figure out some carbon dating, using these decay rates. All right, you know what, I'll let you work on these ones for yourself here, okay? Think about the decay or growth rate and how you can put that into a formula and finding the geometric sequences. All right, well, I hope this helps for your homework and for studying.